Welcome to another video lecture. In this video lecture, we will discuss about the root locus. Now, the root locus is invented by W.R. Evans in 1948. This method is basically gives an idea about the absolute stability and to some extent the relative stability of a control system. And it is a very important tool in analyzing and designing of control system by adjusting the value of gain k of the control system. Now, the definition of root locus is it is the locus. So, it is the locus of closed loop poles obtained when the system gain k varies from 0 to infinity. So, when we vary value of k from 0 to infinity, the locus of the closed loop poles is the root locus of the control system, or we can say in other terms the plot of the locus of roots of the characteristic equation with respect to gain k is the root locus of the system. Let's take one example. What exactly is the root locus? So, suppose we have a unity feedback system with gs. Gs is given as k by s, and it is we need to calculate the root locus for this system where gs is k by s, and since it is a unity feedback system, the value of hs is 1. Now, to calculate the root locus of the system, first we need to calculate the characteristic equation. So, we know the characteristic equation is 1 plus gs hs equals to 0. So, this will be 1 plus gs is k by s and hs is 1. So, this will be multiplied by 1 equals to 0. So, we have s plus k equals to 0. This is the characteristic equation for this system. Now, the locus of the roots of this characteristic equation gives the root locus. So, in order to draw the root locus, first what we need to do, we need to draw a pole 0 diagram for this characteristic equation. We know what is pole 0 diagram, already discussed in previous classes. So, this here we have a real axis, and this vertical axis is the imaginary axis, j omega axis. Now, for different values of k, when k varies from 0 to infinity, the value of closed loop poles is the or the locus of the closed loop poles is the root locus. So, let us assume that value of k varies from 0 to infinity, and we are determining value of s. So, it goes from 0, 1 to up to infinity, and the value of s will be at k is equal to 0, the value of s will be 0. For k is equals to 1, it will be minus 1. For 2, it will be minus 2 up to minus infinity. So, if we draw these values of s on this pole 0 diagram, the locus of this s will be the root locus. So, for k is equal to 0, we got a pole at origin, k s is equals to 0, and for k is equals to 1, we get minus 1 s equals to minus 1. For k is equals to 2, we get minus 2, and so on up to minus infinity. So, this entire negative real axis is the root locus for this system, which is represented by this gs equals to k by s. So, this is how we determine the root locus. For the complex problems, we have some set of rules to calculate the root locus. So, let us discuss the rules to construct root locus. So, the first rule of root locus is, let me write here. So, the first rule is the root locus is symmetrical about the real axis. So, let me write it. Root locus is symmetrical about a real axis. Since we plot root locus on pole 0 plot, so suppose this is the pole 0 plot, this is real axis, this is imaginary axis. What we mean by symmetrical about real axis is this real axis act as a mirror. So, whatever the shape of the root locus on the positive side, the same will be the just mirror image of this will be on the negative side. So, root locus is always symmetrical about the real axis. This is the first rule to construct root locus. The second rule is the starting point and the ending point. So, the starting points of root locus is always the poles, and the terminating points, or we can say ending points of root locus will be either zeros or infinity. So, root locus always starts from the poles and it terminates on either zeros or infinity. And if number of poles is capital P, and if number of zeros is capital Z, and if we assume that P is greater than Z, in this case the total number of branches in the root locus will be capital P, and number of branches terminated at infinity will be equals to P minus Z, and number of branches terminated at zeros will be capital Z. So in the second rule, we discussed that the starting point of root locus will be poles, the ending points will be either zeros or infinity, and if the number of poles is capital P and number of zeros is capital Z, and if P is greater than Z, then total number of branches will in the separate branches in the root locus will be capital P, number of branches which terminates at infinity will be P minus Z, and the number of branches terminated at zeros will be capital Z. Now the third rule is, now the rule number 3 is root locus on real axis. So which part of root locus will lie on the real axis? So a point is on real axis is said to be on root locus if to the right side of the point the sum of open loop poles and zeros is an odd number. Now to understand this, let us take one example. Suppose we have GS equals to K S plus 2 S plus 6 divided by S plus 4 S plus 8. Now this problem we need to find out which section of root locus lie on a real axis. Now there are zeros, so suppose if I want to calculate the zeros, the numerator term when we equate to 0, this will give number of zeros, so this will be S is equals to minus 2 and minus 6 are the zeros. Poles in this problem is S is equals to 0, denominator equals to 0 will give the poles, so this will be S is equals to 0, minus 4 and minus 8, and we already discussed that zeros are represented by O and poles are represented by X. So here we can say number of zeros capital Z is equals to 2 and number of poles capital P is equals to 3, and the number of separate, since P is greater than Z here, like in the second step we already discussed, if P is greater than Z, then capital P is the number of separate branches of root locus, number of separate branches of root locus. So in this case this will be equals to 3. Now to calculate a root locus on a real axis, which part of a root locus will lie on the real axis, let us draw the pole 0 plot for this particular example. So we have a real axis sigma, and this is the imaginary axis j omega axis, and we will locate all these roots on this pole 0 plot. So we have at S is equals to 0 we have a pole, S is equal to 0 we have a pole, at S is equals to minus 4 we have we have another pole, and at S is equals to minus 8 we have, let us extend this further, so x is equals to minus 8 we have another pole. So these are the three poles, S is equals to 0, minus 4 and minus 8, and we have zeros at S equals to minus 2. So we have zeros at S equals to minus 2 and S equals to minus 6 we have another 0. So I have located all the roots of this characteristic equation on the pole 0 plot. Now I want to determine which section of root locus lie on real axis. So we have, suppose this is the first, let me highlight this part. So this is the first section here from 0 to minus 2. This is the first section I am talking about. So from 0 to minus 2, suppose we have a point here, suppose, and we want to find out whether this point lie on the of this root locus lie on the real axis or not. So what we will do, we will assume an imaginary line, vertical line parallel to the imaginary axis, and then to the right side of this line we will count total number of roots. So on this left side, the total number of roots, there is a single pole here. So the total number of poles to the right side of this point is 1, which is an odd number, So we can say this section from minus 2 to minus 1, let me again highlight this. From minus 2 to minus, 0 to minus 2, this section will lie on the root locus. Since the total number of roots is 1, which is an odd number. So on this section 0 to minus 2 will lie on the real axis. Now again we will go further. Let us assume a point from minus 2 to minus 4, suppose here. So suppose I'm talking about this point, let me again write this, and again I'm drawing a vertical line parallel to imaginary axis, and to the right side of this line I'm counting total number of roots once again. So in this case there are two roots. At -2 there is a 0, and at 0 we have a pole. So in this case the total number of roots is 2, which is an even number. So we can say from -4 to -2 there will be no part of root locus which lies on the real axis. So from -4 to -4 to -2 there will be no root locus branch on real axis. Similarly, if I go further from -4 to -6, suppose I have a point here, and again I am drawing a vertical line parallel to the imaginary axis, and on the right side of this line I am counting total number of roots. Again the total number of roots is one pole at -4, 1 0 at -2, and 1 pole at 0. So there are 3 roots, which is an odd number. So we can say from this that from -6 to -4 the root locus will lie on the real axis. Okay, so let me again draw this pole 0 plot and highlight the section where the root locus exactly lies on the real axis. So we have a pole at 0, we have a pole at -4, we have a pole at -8, and we have zeros at -2, and we have 0 at -6. So let me again draw this the different line. On this section, root locus we consider the root locus will lie on this section of real axis, and we also discussed that root locus originates from the pole and it terminates at the 0. So this will go like this. This branch will go like this, and from -4 to -2 we discussed that root locus will not lie on this real axis, and again we discussed that -4 to -6 root locus will lie on the real axis, and again it will originates from the pole and it terminates at the 0. And again if we'll count the roots, then we will say that from -8 to -6 root locus will not lie on the real axis. And for the last section from -8 to -infinity, for -8 to -infinity, this section again if you will count the total number of roots on the right side, you will get odd numbers. So we can say the root locus will lie on this section. It will start from -8 and it will terminate at -infinity. So these are the 3 sections. This is the first section, this is the second section, and this is the third section. So these are the 3 sections of root locus which lies on the real axis. So I hope you understood this point. Now the rule number 4 is angle of asymptotes. Angle of asymptotes. Now what is asymptotes exactly? So we already discussed that there are p minus z branches of root locus, which terminate, or we can say terminating at infinity, and these branches will go along a certain straight lines. These lines are known as asymptotes. So as already discussed that certain branches of root locus will terminate exactly p minus z branches of root locus will terminate at infinity, and these branches will go along some straight lines. These lines are known as the asymptotes. Now to calculate these asymptotes, we will calculate the angle at which these asymptotes are originating. So the angle theta, angle of asymptote theta, is given as 2q plus 1 multiplied by 180 degree divided by p minus z, where q is an integer value, starts from 0, 1, 2, 3 up to so on. So let us suppose that in a particular question we have p minus z equals to 3. In that case we will have 3 branches of root locus which terminates on infinity, and suppose z is equals to 0, and then in that case 3 branches will terminate at infinity, and we need to calculate the angle of asymptotes. 3 asymptotes will be there, and we need to calculate the value of angle of asymptotes. In this case the first value theta 1 will be equals to 2q will be 0, that case, plus 1 divided by p minus z is 3 into 180. So this will gives us the 60 degree, and when q is equals to 1, we will get the second angle of asymptote. This will be 2 into 1 plus 1 divided by 3 into 180. So, this will be 180 degree, and theta 3 is calculated when we will put q is equals to 2. So, this will be 2 into 2 plus 1 divided by 3 into 180 degree. So, this will be 300 degree. So, these are the three angle of asymptotes for this case when p minus z is equals to 3, and all these three branches are terminating at infinity. The rule number 5, let us discuss rule number 5 here. So, rule number 5 is about centroid. What exactly is centroid is? It is the intersection point. Let me write here. It is the intersection point of the asymptotes on a real axis or with the real axis. So, to calculate centroid, C is equals to summation a real part of open loop poles, all the open loop poles, minus summation real part of open loop zeros divided by p minus z. To calculate the value of C, it is a coordinate on the real axis. So, let me again write it. Centroid is always real. So, this is a coordinate on a real axis. So, to calculate this coordinate, what we will do, we will add all the real parts of the open loop poles, and we will add all the parts of open loop zeros. Then we will subtract these two values and divide it by p minus z. So, that is how we will calculate the centroid. We will take a few examples later on to discuss how to calculate these values, centroid and angle of asymptotes, etc. Now, the rule number 6 is about breakaway point. Let me write here. Let me again select the pen. Okay, so now the rule number 6 is about breakaway point. So, what exactly is a breakaway point? It is a point, or you can say point, where multiple roots of the root locus occurs. Now, let us suppose a situation where we have a pole 0 plot. This is real axis, this is imaginary axis, and we have a pole at s is equals to 0, we have a pole, and again s is equals to minus 1, we have a pole, and there is no root in between these two values, minus 1 and 0. And we already discussed that root locus always starts from the pole. So, this will be starting point. Again, this will also be starting point. Then where exactly the root locus will terminate? The root locus will terminate at the breakaway point. So, there will be a breakaway point in between these two roots, these two poles, at s is equals to minus 1 and s equals to 0. There will be a breakaway point in between these two values, minus 1 and 0. And at this point, the branch of the root locus will go from real to complex. So, this will, suppose there is a root locus at this point, and at this point the branch of the root locus will go from real value. On the real axis, the value of the root locus is real, and it will go to complex. It will convert it into complex value. So, we can also say a breakaway point is the point where branches break into the complex value from the real value. So, how to calculate the breakaway point? So, there are some steps to calculate breakaway point. What we will do, let us write. First, we need to find the characteristic equation 1 plus gs hs equals to 0. We will find the characteristic equation. In the second step, we will write the equation in the form of k. We will write this equation in the form of k. Then in the third stage, we will calculate dk by ds. We will differentiate this equation with respect to s, and then we will equate to 0. We will find dk by ds equals to 0. Now, the roots of this equation dk by ds equals to 0 will give the breakaway point. So, again we will discuss these all steps when we will take examples later on. Rule number 7 is about the intersection point with the imaginary axis. Let me write. So, rule number 7 is the intersection of root locus with imaginary axis. To calculate the intersection points on imaginary axis of the root locus, what we will do, there are again set of rules. The first step is construct the characteristic equation 1 plus gs hs equals to 0. In the first step, we will construct the characteristic equation. In the second step, we will construct the Routh array in terms of k. We will construct the Routh array in the second step. In the third step, we will determine the value of k. Let me again select this pen. So, we will determine the value of k which makes any row of this Routh array equal to 0. So, these values of k are known as k marginal, which makes any row of the Routh array equals to 0. These values of k equals to k marginal. In the next step, we will construct the auxiliary equation as just above the row 0 row of Routh table, and the roots of this auxiliary equation as equals to 0 will give the point of intersection of root locus on imaginary axis. So, these are the steps to calculate the intersection point of root locus with imaginary axis. So, again we will discuss these all steps in the next lecture when we take examples. The last rule to construct root locus, the rule number 8, is about angle of departure and angle of arrival. So, rule number 8 is angle of departure and angle of arrival. This step number 8 is only applicable. Let me again write this step. This step is only applicable for complex roots. If there is no complex roots in the problem, then this step number 8 is not applicable. So, this step is only applicable for the complex roots. Again, second point, departure angle will be determined for complex poles, since the root locus originates from the poles. So, the departure angle will be determined for the complex poles, and arrival angle will be determined for the complex zeros, since the root locus terminate at the 0. So, the arrival angle will be determined for the complex zeros. Now, to calculate the departure angle phi d, let us suppose the departure angle is phi d. It is given by 180 degree minus phi, where phi is summation phi p minus phi summation phi z, where summation phi p is the contribution. Let me write here, contribution by angles made by remaining open loop poles, and summation phi z is contribution by angles made by remaining zeros, open loop zeros. And to calculate angle of arrival phi a is equals to 180 degree plus phi. This again phi is summation phi p minus phi z. So again, to understand how to calculate the angle of departure and angle of arrival by these expressions, we will take examples in the next lecture. To summarize all this, let me again take the next slide. Now, to summarize all these points, what we will do to construct a root locus, first let me select the pen. Okay, so the first we will find capital P, number of poles, number of poles is capital P, number of zeros is capital Z, and then we will find P minus Z, the starting point which is the poles, and the ending points which is the zeros. So in the first step we will calculate number of poles, number of zeros, P minus Z, which is the separate branches of the root locus, the starting points which is the poles, the ending points which is either zeros or the infinity. In the next step we will draw the pole zero plot and find the section of real axis where root locus exists on, or you can say on root locus, or the part of root locus which lie on the real axis. In the next step we will calculate angle of asymptotes. In the next step we will calculate the centroid. Next step we will calculate breakaway point. In the next step we will calculate the intersection of root locus with imaginary axis, root locus intersection point. In the next step we will calculate the angle of departure and arrival, and in the final stage what we will do, we will combine all the steps, and construct the root locus. Now, depending upon the problem, there may be some problems in which there are no complex poles and zeros. In that problem we do not require this step, and in some problem there will be no consecutive zeros and poles on the real axis. In that case we do not require to calculate the breakaway point. So depending upon the problem, there may be we don't need to calculate all the steps to draw the root locus. So I hope you understood these rules to construct the root locus. In the next lecture we will take few examples to construct how to construct the root locus. Thank you.